You ever wonder how your GPS just knows the fastest way to get somewhere? Well, the secret sauce, believe it or not, is hidden inside a brain teaser that's over 1,000 years old. Today, we're going to connect the dots and see how solving this ancient riddle is the key to unlocking the logic behind the tech we use every single day. Okay, so let's dive right in with a super classic puzzle, one that's been stumping people for centuries. It's the one about the farmer, the wolf, the goat, and the cabbage. So the setup seems pretty straightforward, right? You've got a farmer, and he needs to get his wolf, his goat, and a cabbage across a river. The problem is, he's only got this tiny little boat. And of course, there's a catch. And that catch is where all the fun begins. All right, here are the rules of the game, and this is what makes it so tricky. First, the boat can only hold the farmer and one other item. That's it. But the real problem? You've got a food chain situation on your hands. If you leave the wolf alone with the goat, well, goodbye goat. And if you leave the goat alone with the cabbage, goodbye cabbage. The only way everyone stays safe is if the farmer is there to supervise. So the big question is, how does the farmer get everyone across the river safely? Go ahead, take a second and think about it. It's definitely trickier than it first appears. You really have to think a few moves ahead. And, hint hint, you might even have to take a step backward at some point to move forward.
Okay, so the real trick to solving this isn't just randomly trying things until you get lucky. Nope, there's a much smarter way, a systematic way, and it all begins with drawing a map of every single possible move.
And in the world of computer science, this kind of map has a special name. It's called a graph. Think of it like this. Every possible situation, let's say the farmer and goat are on one side while the wolf and cabbage are on the other, that's a node or a dot on our map. And the lines that connect those dots, the edges, those are the legal moves the farmer can make. And here it is. This is the complete map for our farmer's puzzle. You can see everything laid out, the starting point, all the dead ends where, oops, something gets eaten, and right there, the one successful path that gets everyone across safely. By turning this brain teaser into a graph, the solution just kind of pops right out at you. Now, in our little river puzzle, every trip across was basically the same. But what if some trips took way longer or were harder? You know, in the real world, not all paths are created equal. And that's where our simple map needs a serious upgrade. I mean, just think about your drive to work or school. Is the path with the fewest turns always the fastest? Heck no. Not if it's jammed with traffic or has a stoplight every 10 feet. Sometimes, taking that longer route is actually the way to go. So check out this example here. The straight shot from A to B looks great, but it has a really high cost. Maybe that's a crazy toll road or a super steep hill. But look at this other path, the one that goes through C and D. It's got more steps, sure, but the total cost is way, way lower. This is exactly the kind of problem our new upgraded map needs to figure out. And this brings us to what's called a weighted graph. It's pretty simple. Every path, or edge, has a number assigned to it, a cost. That cost could be anything: time, distance, money, you name it. And now, our goal isn't just to find the path with the fewest steps, it's to find the path with the lowest total cost. So, how do we do that? Well, this brings us to the hero of our story, a really clever and super efficient algorithm built to do exactly this. It's called the Uniform Cost Search, or just UCS for short. The whole strategy behind UCS is incredibly simple, but really powerful. It's just this. Always explore the cheapest path available so far. That's it. Imagine you're at a crossroads, right? UCS looks at all the paths it knows about and always picks the one that has cost the least amount to get to up to that point. Okay, let's actually watch this thing in action. Our goal is to find the cheapest path from point A to point F. The way the algorithm works is by keeping a kind of to-do list, and it's a priority list. It always keeps the cheapest path it's found so far right at the top. So we start at A. It's the only thing on our list, and the cost to get there is, well, 0. Okay, so from A, the algorithm sees it has two choices. It can go to B, which has a cost of 0.9, or it can go to C, which costs just 0.1. It puts both of these options on its to-do list. Now, it looks at the whole list and asks, what's the absolute cheapest option I have right now? Well, that's the path to C, so that's where it decides to explore next. All right, now we're at C. From here, it finds a path to D, and it calculates the total cost to get there. That's the 0.1 it took to get to C, plus the 0.1 to get from C to D. So the total cost for the path ACD is 0.2. It adds this new path to its to-do list, and again, it checks the whole list. Right now, that path to D is the cheapest thing on there, so it knows its next move is to explore from D. Now, when it gets to D, something really cool happens. First, it finds a path to our goal, F. But it doesn't stop. It also finds a new path to B, and the total cost is only 0.4. Now remember that first path to B that costs 0.9? The algorithm is smart. It sees this new route is way better, so it updates its to-do list. It basically says, scratch that old expensive path to B, I found a cheaper way. And the algorithm just keeps doing this over and over. It looks at its list, pulls the cheapest path off the top, explores from there, and adds any new paths it finds. And here's the crucial part. It only stops when the number 1 item on its priority list, the absolute cheapest path it knows about anywhere in the graph, is a path to our destination, F. And bingo, there's our answer. The cheapest path is A to C to D to F. And because of the way it works, because it only stops when the goal is the cheapest option overall, we can be 100% certain that there isn't some other, sneakier, cheaper path hiding somewhere. It's guaranteed to find the best one. So I know this might feel like a kind of abstract little puzzle, but this exact logic, this is the engine behind a piece of technology that I bet you use almost every single day. Yep, every single time you pull out your phone and ask for the fastest route, an algorithm just like UCS kicks into gear. Your phone sees the entire road network as one gigantic weighted graph. Every intersection is a node, and the cost for each road is calculated using distance, speed limits, and even live traffic data. It then solves this massive shortest path problem for you in like seconds. And it's not just for getting you to your appointment on time. This idea is everywhere. It's how Amazon figures out the cheapest way to get a package to your door. It's how the internet works. When you send an email, this kind of logic finds the least congested path for your data to travel across the world. It's even used in social networks to figure out how you're connected to other people. And that's really the beautiful connection here, isn't it? This simple, elegant idea of turning a problem into a map and then methodically searching for the best path, an idea we first saw with a farmer, a goat, and a cabbage, is the very same tool that powers these enormous, complex systems that run our modern world. It's just such a powerful reminder that some of our most futuristic technologies are actually built on these timeless, ancient principles of pure logic. And it really makes you wonder, right? If an old riddle and your phone's GPS share the same core DNA, what other ancient ideas are out there, hiding in plain sight, quietly shaping the world all around us?